With the recent rise in gas prices, a lot of people are looking for a better way. What if your car could get all the power it needs from water and sunlight? Fantastic as it sounds, that day may have just gotten a little closer thanks to a discovery in a chemistry lab at the Massachusetts Institute of Technology. This MIT lab has something few others on campus can boast: a theme song.
Here, what can I tell you? They're bubbles. You can see them.
The reason for the music and high spirits is this simple little device, or rather, what's happening inside it. Those tiny bubbles are evidence of a chemical reaction that might one day help the world kick the oil habit and curb global warming.
In my experience, this is pretty good for anything I've ever done in my life, and my group's had some big advances before.
Dan Nocera was a chemistry grad student during the last energy crisis in the late 1970s. He saw the long lines at gas stations and decided to make energy the focus of his career. Today, he's the Dreyfus Professor of Energy at MIT and a leader in the field of artificial photosynthesis. His approach to solving the world's energy problems is to take a cue from plants.
Because these leaves know how to take sunlight and make chemical fuels efficiently. And so we try to understand as much as we can about how this is doing it to say, can we duplicate that in the lab with some man-made materials?
Photosynthesis involves a series of cycles and reaction centers so complex it seems to have been inspired by Rube Goldberg. But Nocera isn't trying to duplicate the whole process, just the part where the plant splits water into hydrogen and oxygen.
Water itself is a lousy fuel. It doesn't have much energy in it. But if I can take water plus a sunlight input, I can take the bonds of water and rearrange them and get OO bonds, oxygen bonds, and HH bonds, hydrogen. And that's a fuel. The hydrogen will burn with the oxygen, and now that energy that was rearranged in the high energy bonds of hydrogen and oxygen is released, and you can power your planet with it.
To pry apart those hydrogen and oxygen atoms, plants convert sunlight into an electrical current that courses through the leaf. And people have long put electricity to the same use. English chemist William Nicholson split water more than 200 years ago, just a few months after the invention of the battery. And countless chemistry students have done it using an electrolysis device like this one. When a voltage is applied, the flow of electrons makes hydrogen gas, H2, at the negative electrode, and oxygen gas, O2, at the positive. But a lot of energy is needed to split each water molecule. The water-splitting device in Nocera's MIT lab works just the same way.
So what we have here is an electrochemical cell.
With one key difference. Postdoc Matt Cannon has added a special ingredient that speeds up the formation of oxygen.
Matt, are there bubbles coming
It's what chemists call a catalyst.
The catalyst that produces oxygen is a dark layer on the bottom half of this glass slide. And you can see bubbles sticking to the surface and then some of them slowly escaping from the surface as the catalyst is operating.
Splitting water is like crossing a mountain range. To get from start to finish, you have to spend a lot of energy getting over the top, unless you can find a shortcut. The MIT catalyst is the chemical equivalent of a hidden pass through the mountains. It doesn't eliminate the whole climb, but it cuts off about 2/3 of the energy peak, the excess voltage needed to make the reaction go. That's a big improvement. And while many previous catalysts have been made from precious metals like platinum, this one is made from cobalt, oxygen, and phosphorus.
These are really earth-abundant materials. This is stuff you find in rocks. And so that means you can think of using a lot of this for the energy problem. You can't do that with platinum.
Hydrogen fuel cell vehicles use no petroleum and emit only water vapor.
The MIT discovery could heighten interest in the so-called hydrogen economy, powered by devices called fuel cells. There's no ordinary engine under the hood of this GM car. Its power comes from a fuel cell that combines hydrogen and oxygen chemically.
The Honda FCX Clarity is a zero-emission vehicle. And
even so, cars like these do little to curb global warming, because most hydrogen now comes from oil, coal, or natural gas.
You get hydrogen from fossil fuels, you're making CO2, so fuel cells don't solve the problem. Fuel cells only help with the problem when you get your hydrogen from a non-carbon-based source, water. Unfortunately, if you want hydrogen out of water, you can't go in there thinking, I'll only get hydrogen. You need to get that oxygen, and guess what? It's the oxygen that's been the tough nut to crack.
In his long search for a water-splitting catalyst, Nocera had promising results with rare metals like rhodium and iridium. But for a practical catalyst, he knew he'd have to look elsewhere in the periodic table.
Along a given column, the metals have the same types of properties. So we were down in iridium and rhodium, and if you'll look up at the top, guess who's sitting up there? Cobalt. And that's a cheap metal.
Cannon set out to investigate by making a complex compound of cobalt, nitrogen, carbon, and hydrogen. This would be his catalyst. To soak up acids formed during the reaction, he added a buffer of phosphate, a common compound of phosphorus and oxygen. Then he inserted his glass electrode and turned on the power, hoping his catalyst would start generating oxygen.
But what I noticed is that over time, the electrode acquired this thick coating, which shouldn't be happening if the molecule is in solution, and it initially forms kind of a golden green layer over the course of 15 to 30 minutes, and then it becomes darker and darker over time, and after about an hour, you see bubbles emanating from the surface.
This was not the result Cannon hoped for. It meant his carefully crafted cobalt compound was falling apart, his experiment a failure. But there were those bubbles. Could they be oxygen?
It was too tantalizing to walk away from, and he said, I need to understand this much more deeply.
And what I subsequently realized was that I don't need to make this synthetic compound. It was really just the cobalt that was essential.
Somehow, the cobalt and the phosphate buffer were spontaneously forming a layer of material on the slide, and it was acting as a catalyst to make oxygen from water.
So when did you make this electrode right here?
Cannon went to Nocera with his findings.
Dan's first reaction was to say, well, what is it? I said, I don't know how it's working. I don't know what its structure is, but here's what it does.
Nocera was skeptical. It seemed too good to be true.
Where I got really excited, where I thought we had something, is when I went in and looked and saw those bubbles streaming off the electrode. And so it's really that visual. It was the visual that I said, whoa, this is, we have something here.
Nocera and Cannon believe the cobalt and phosphate form an amorphous layer on the slide.
Under the microscope, you can see cracks in the film because when it dries, just like mud, it tends to crack. But the film itself is composed of a bunch of smaller particles that have all essentially meshed together.
But if he keeps it going for a long time, you'll see little spheres building on the surface because we think this is really a dynamic surface. It's not static. And that's one of the keys also, I think, that makes this work.
Given the similar techniques used in the electroplating industry, Nocera believes the new catalyst may be easy to scale up.
The way Matt makes it is he just puts cobalt ions and phosphate in solution, turns the potential to 1.5 or 1.6 volts, it electrode deposits, and then it starts making oxygen. This is a really easy thing to manufacture.
Nocera looks forward to the day when mass-produced devices built around the cobalt catalyst are powered by photovoltaic solar cells. The result? A totally renewable energy system with no greenhouse emissions.
H2O plus light gives us hydrogen plus oxygen. Hydrogen plus oxygen gives us energy and water back again.
Such a system would convert sunlight into a useful form of chemical energy, just like plants do.
Actually, so that's a good point.
Nocera is quick to acknowledge that day is years away.
I think it's actually a liability because the heavier
it gets,
the catalyst gets.
Many questions remain to be answered. Many engineering challenges lie ahead.
You're looking at the genesis of discovery. I wish I could run around the streets going, woohoo, but I can't because I don't know quite what we have.
The discovery here is...
But these are new concepts that will advance the field, even if this thing quite doesn't measure up. It's a eureka moment for us. And it really has opened our eyes to a new path, which I hadn't been pursuing in my group, and I will be, and I have a feeling a lot of other people are going to be now.